In this video, I'm going to look at two example problems for finding volumes of solids of revolution. And so for both these problems, examples 2 and 3, we're going to use the same region. So bounded by the graphs y equals 2 squared of x and y equals x in the first quadrant. So y equals x, of course, is pretty easy. It's, it goes through 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, and so on. So we've got that line y equals x. Y equals 2 square root of x. Well, we can pretty easily plot some points. If I plug 0 in for x, square root of 0 is 0. If I plug 1 in for x, square root of 1 is 1, so 2 times 1 would be 2 for my y-coordinate. And I don't want to plug in 2 or 3 because I don't know their square roots, but if I plug in 4 for x, square root of 4 is 2, 2 times 2 is 4. So we get the points 0, 0, 1, 2, and then 4, 4. And so it's going to look something like this. Now we can see that those are points of intersection. The other way, of course, we could verify that this point 0, 0 and 4, 4 are really where these meet, is we could just set these equations equal to each other. We could set their y-coordinates equal, y equals y. So that would say then that 2 times the square root of x is equal to x. We could square both sides of the equation. 2 squared is 4. Square root of x times square root of x is x. X times x is x squared. So then we've got x squared minus 4x equals 4. We can factor out an x. X squared minus 4x equals 0. We can factor out an x. And then when we solve, we get either x equals 0 or x equals 4. And then, of course, we've got this, the one equation is y equals x. So if the x-coordinate is 0, the y-coordinate has to be 0. And so, we get the points 0, 0 and 4, 4, which is, what we've got here. Those are the points where they intersect. So that's just sort of verifying what we've already done. That's our underlying region. And it says now we're going to rotate that about the y-axis. So I'm going to be rotating in this direction. For this particular region, you would have a choice. We could set up our rectangles certainly to be vertical. That would be like this. If I'm setting it up vertically, then eventually I'm probably going to have to find the length of that rectangle. I would take the y-coordinate at the top. That would be this 2 squared of x. And the y-coordinate at the bottom, which would just be x. Right? The top would be on this graph, so this would be the top y-coordinate. The bottom would be on this graph, so that would be the bottom y-coordinate. And I would just subtract those, and I've already got that set up pretty well. That would be pretty good. If we would want, we could do a horizontal rectangle. That would then, I could take left minus right. Left is always on the square root graph. Right is always on the linear graph, so that would work perfectly fine. So in this case, you would have a choice. It really wouldn't matter. If we set it up this way with a horizontal rectangle, then when I rotate that, I'm rotating perpendicularly to this axis of rotation, right? That's how the rectangle is set up. And so I'm going to get a disc or washer, in this case a washer most of the time because there's a gap between the rectangle and the axis of rotation. So then I'd have to add up the volume of all those washers. Now, in this section, we're officially concentrating on the shell method. However, for example, for section 5.2, in the example problems I did for that, we did this exact same problem, and we're going to get the same answer, but I'm going to do it the other way with vertical rectangles and see that the shell method gives us the same answer that the washer method gave us back in 5.2. So you can go back and review that if you'd like to see that we get the same thing. So my representative rectangle, I'll draw a vertical rectangle here. One thing I know then, that's going to have a delta x, right? So it's a tiny x thickness here. So my variable of integration is going to be x. When I rotate this about the axis here, it's going to give me this sort of shell shape, right? Not shell shock, this sort of shell shape that we would get when I would do that. And so that's the cylindrical shell when I rotate that rectangle in that direction. I don't really want all that there. It's obscuring what I need to see. So I'm going to get rid of that, but that's what I'm going to look at here. We know that the volume of a shell then is the circumference 2 pi r times the height h times the thickness, which in this case would be delta x. So where's the r going to be? Well, r is the distance from this rectangle to the axis of rotation. Right? That's going to be my r. And what we have to remember is to measure that this rectangle is changing. Its location is changing from x equals 0 all the way over here on the left to x equals 4 over here on the right. So we keep track of that just with the variable x. Okay? So my radius is just going to be this distance from x over here. And of course, at this place, we've got that x is equal to 0. For the height, that's going to be this distance. The top is the square root function, 2 square root of x, and the bottom is the linear function, so y equals x at the bottom. So the volume of my shell, my radius is going to be x minus 0. My height is going to be 2 squared of x minus x, and then I have delta x. I'm going to rewrite the square root with a fractional exponent. X minus 0, of course, is just x. Then I'm going to get 2x to the 1/2 minus x, delta x. And so when I distribute the x, that's x to the first, which is x to the 2/2. That's going to be x to the 3/2, and then minus x squared delta x. Okay. So that's sort of my extra work there. So going back to find the whole volume, I can factor out the 2 pi. My integral here, it's in terms of x. So I'm starting at the left at x equals 0. I'm ending up at x equals 4. And I'm going to get this 2x to the 3/2 minus x squared dx. So, to evaluate this, I take the antiderivative. So 2x 3/2 plus 1. I go up 1. 1 would be 2/2. So that's going to be 2x to the 5/2 divided by 5/2 minus x to the 3rd divided by 3, evaluated between 0 and 4. Now, when I divide by 5/2, that's really multiplying by the reciprocal, 2/5. I've already got a 2 in the top, so that's going to become a 4, x to the 5/2. And then my 5 would be in the bottom, right? I'm multiplying, dividing by 5/2 is multiplying by 2/5. So now I plug in 4. And then I plug in 0. Well, 0 to any power is 0. 4 times 0 over 5 is 0. 0 cubed over 3 is 0. So I don't get anything from that substitution. That's not always necessarily true. I've said this before, but always just at least think through plugging in 0 and make sure you actually get 0. Just as an example, if there was a cosine x somehow involved, cosine of 0 is not 0. Cosine of 0 is 1. So plugging in 0 doesn't necessarily give you 0 all the time. So how do I do this? Remember, fractional exponents. The numerator is the power, the denominator is the root. So this 2 says I'm going to take the square root of 4, and then I'm going to take that to the 5th power. So the square root of 4 is 2, 2 to the 5th power is 32. So I'm going to get 4 times 32, that's going to give me 128 over 5. You can check that. Oh, what did I do there? In class, maybe somebody would have said something. So 4 cubed over 3. I don't know why I was doing the 64, I think, in my head. All right, so that's going to be minus 64 over 3. And now I'm going to want to make both of those probably into 15 as a denominator, right? So I'm going to multiply top and bottom by 3, and then top and bottom by 5. So 128 times 3 is 384. 64 times 5 is 320. So I get 64 over 15. And then I multiply in the 2 pi, and I get 128 pi over 15. And again, if you compare to the example problems I did in section 5.2, you'll see this exact problem, and we get the same answer, but we do it using the washer method instead of this shell method. Now, in the next example here, we have the same region, but now I want to rotate about the line x equals 5. So I've got the same basic setup. I still have my line, y equals x. And I have this square root function that's the same. It goes through 1, 2, 4, 4, and starts here at 0, 0. But now I'm going to rotate about this line x equals 5. Okay. So if we wanted, again, we could set up either vertical or horizontal rectangles for this region. We would have a choice. This is another one that I did actually, I believe, in section 5.2 examples, and we did it there with horizontal rectangles and ended up with washers. Here I'm going to do this with vertical rectangles and end up with shells instead. So you can sort of think through what I did on the last one and how the picture came. If I rotate this rectangle around this axis, it's going to give me that kind of cylindrical shell. And so for the volume of the shell, it's going to be the circumference, 2 pi r, times the height, times the thickness. And of course, again, this is a little thickness in the x direction. That's how my rectangle here has been oriented, so that that little thickness is an x thickness. To find r here, you know, if I remember, this rectangle is tracked with my variable x. I'm going to let x start here at the left at x equals 0 and end up here at x equals 4. So x in the integral tracks where this rectangle is. For the radius is this distance here. It's important then that I keep in mind that this is the line x equals 5. And so if I want to find this radius, it's a horizontal distance. To find a horizontal distance, I always take the right x-coordinate minus the left x-coordinate. The right x-coordinate here is 5. The left x-coordinate is just x. So my radius is 5 minus x. The height, of course, then, is going to be the distance, the height of that rectangle, and the top is this 2 square root of x, and the bottom is just x. So 2 square root of x minus x delta x. Okay, I'm going to write my square root as a fractional exponent. So that's x to the 1/2. And now I'm going to distribute, I'm going to do FOIL with those binomials. So 5 times 2, 10, x to the 1/2, that's first. Outer, 5 times negative x, negative 5x. Inner, I get negative x times 2x to the 1/2. So this is x to the first, that's really x to the 2/2. X to the 2/2 times x to the 1/2 will be x to the 3/2. So minus 2x to the 3/2. And then negative x times negative x is positive x squared delta x. So that's sort of my setup for this problem. So to find the overall volume, I'm going to pull out the 2 pi. We're going to integrate as x goes from 0 to 4. And I've got 10x to the 1/2 minus 5x minus 2x to the 3/2 plus x squared dx. So I'm going to have to take the antiderivative. So 1/2 plus 1, right? We have to take this exponent, go up by 1. 1/2 plus 2/2 would be 3/2. So I'm going to get 10x to the 3/2, but then I have to divide by that new exponent. 5x to the second, divide by the new exponent. Let's see, 3/2 plus 1, 3/2 plus 2/2 would give me 5/2. And I have to divide by that new exponent. So dividing by 3/2 is multiplying by 2/3. So 20x to the 3/2 over 3 minus 5x squared over 2. Dividing by 5/2 is multiplying by 2/5. So 2 times 2, 4. X to the 5/2 over 5. Alright, let's see. I think I'm going to have room here if I come down a little. So now I'm going to plug in 4. So I just plug 4 in for every x. And then I have to at least think, what happens if I plug 0 in for every x? Well, in each case here, 0 to a power is 0, so I get a whole lot of nothing. So 4 to the 3/2, again, remember, square root of 4 cubed. So square root of 4 is 2, 2 cubed is 8, 8 times 20 is 160. 5 times 16 is 80. 4 to the 5/2, the square root of 4 to the 5th power, right? Square root of 4 is 2, 2 to the 5th power is 32, 4 times 32 is 128. Okay. So what do we have here? Well, I could put together my thirds. 160 plus 64 would be 224 over 3. 80 over 2 is 40. And I still have the 64 over 3. If I want to switch everything maybe to a denominator of 15. Oops. No, I already did that. Wait. Not 64 over 3. I already put that in. I've still got the 128 over 5. Oops. There. Now I want to get a denominator of 15. With the 40, I can think of that as 40 over 1 and then multiply top and bottom by 15. So 224 times 5 is 1120. 40 times 15 is 600. And 128 times 3 is 384. And when we combine these together, we get 136 in the top and 15 in the bottom. So if I distribute in the 2 pi, we get 272 pi over 15. And again, if you compare that with an example I did in section 5.2, you'll see that it's the same answer.